this is machine learning. In the first lecture, I got through about 2/3 of an overview of machine learning, and the points I tried to emphasize were that it's all very easy, and that you can kind of break down the subject into 3 points. Basically, machine learning is just curve fitting with some function with a huge number of parameters. So the first thing you need to know is sort of what is the function that you're going to use. And we said that if your data is in the form of some very high dimensional vector, and you want your data to be in that form if you want to use these techniques, so you should use data in that form, then you can just compose, you can just use linear algebra plus some very, very simple nonlinearity. There was this function max 0x, which is one of the simplest nonlinear functions you can imagine. And you can just repeatedly compose linear transformations with this function, and you get some general class of nonlinear functions. There are these neural network parameters theta, which are just the matrices involved and some affine offset, so you just get wx plus b. These are the neural network parameters. They're called weights and biases, and that is the space of functions that we use. Maybe as some component of today and tomorrow, I'll tell you about some more complicated functions you can make this way, but this is really the sort of basic ingredient. The second step then is what is the goal? What is the goal of learning? And what is learning? Well, learning just means trying to figure out values of w's and b's that produce a function that computes something that's interesting to you. Like generating images, or maybe generating fake LHC events instead. Whatever, you want some way of writing down a function or a functional of this neural network and your data that that can be optimized with respect to these parameters so that you get a good result. And so this is usually called a loss function. And loss, because big values of loss is bad, so you want to minimize the loss function. And there are examples like just least squares, which everyone has seen at some point in their life. And also, there's also maximum likelihood. If your neural network produces numbers that get interpreted as probabilities, then you can write down a loss function, which is which I wrote as minus log probability of the particular label of the data, and this is the kind of loss function you can use for classification. I also said that this is the part of the subject I'm going to talk about least, because I think it's most well treated by references all over the place. It's also the area that is under best, most sort of rigorous mathematical control. Statisticians have thought a lot about this kind of question for a long time, and so they have very clear answers with very clear logic behind them, and you can read about it. I sent out some links for you to play with. One of them is to my course notes and to some other notes on this subject. So the specific things you should read about if you're interested to sort of understand this in more details, you should understand very basic information theory. So of course you know what the entropy is in physics. There's entropy in information theory. There's also something called the KL divergence by computer scientists. It's called the relative entropy by physicists, and you should understand what that is. And then there's a couple of other basic statistics things that are worth understanding, like what bias and variance are and things like that. But that's sort of what you need to know to understand this. And I'm going to basically avoid talking about it for the next few lectures. The other thing that I emphasized about sort of this step of the question is that the different kinds of machine learning, supervised learning, unsupervised learning, and reinforcement learning, are basically differentiated by how easy it is to express this objective. So in supervised learning, you have data and it has a label, and so you have this label to provide supervision. In unsupervised learning, naively, it's extremely hard, but you usually make progress by reformulating it as though it's something like supervised learning. So for example, you can try to predict the sequence of words in a sentence. And in that sense, even though it's unsupervised learning because you're learning to write, you turn it into supervised learning because all you're doing is trying to predict the next word that's going to appear. And then there's reinforcement learning, which is the part of this subject I'm also not going to talk about, which is how you make an agent that plays games like Atari or Go, things like that. There, you don't know what the best move is, but you know whether you won or lost at the end of the game. And so there's a big distance between what the function is computing, which in the case of reinforcement learning, like playing a game, is like what move to make in the game, and the loss, which is whether or not you won or lost the game. It's hard to attribute success or failure to individual moves, etc., and that makes it harder. I sent you in this email some references if you're interested in learning more about that, but I'm not going to talk about it. And then the third step I mentioned is the optimization process, which is how you practically, computationally, given that you have this function parameterized by w's and b's, and given that you have some loss function that you want to minimize with respect to w's and b's, given the data, how do you actually find the minimum? And I mentioned that basically all of the ways that you do this are elaborations on just plain old gradient descent. You compute the derivative of this objective with respect to the parameters, and you take little discrete steps towards the minimum. And roughly speaking, that's it. So that was where we got so far in this overview. I'm going to talk a little bit more about a few aspects of machine learning at a sort of overview level. So one question that you might have about this optimization, practically speaking, is what do you actually have to do? So if you're like me, you might have thought, oh, wow, okay, so I guess this is really a big pain, because I guess I write down this neural network, but then I have to go in Mathematica or by hand, and I have to compute what all of the derivatives of this function are, and then I have to like write a computer program where I enter in what all of those derivatives are with respect to all these parameters, and then finally I can sort of run the program. And if I want to tweak what the neural network is, maybe I have to change what that process is. So that's one of the first things you might think. So in other words, there's a question of how do we compute the gradient with respect to theta of the loss. And one thing that you could do, one of the first ideas you might have, and you could accomplish it, is you could compute this derivative symbolically for a given neural network. And I mean, it's actually a useful exercise to go through and do this once for some simple neural network, just so you understand what exactly it has to do. But it turns out that this is not the way that the field works, and this is a great relief because it means that instead of having to go through that step, you just don't have to. All you have to do is tell your Python code with TensorFlow or PyTorch or whatever it is that you're using what the function is you want to compute, and it'll compute the derivative automatically. So the next thing you might think is, oh wow, it computes the derivative automatically. Well, I know what derivatives are. They're sort of like finite differences in a limit. So you might think maybe what it's doing is it's doing some clever thing, like it's defining f prime of x as something like f of x plus epsilon minus f of x over epsilon. I mean, maybe you guys are not as naive as me, but this is what I might have thought if I knew, if someone told me initially, well, you don't have to do it symbolically, the computer just knows how to compute the derivatives itself. Finite differences seem like a reasonable thing to do. But this is also definitely not what your computer will do if you try to train a neural network using the free libraries that are available to do this. So why is this a very bad idea? Well, it introduces lots and lots of horrible rounding errors. As an example, I mean, your function f of x could be something like 10 to the 10 plus x squared, and you want to compute something like f prime of 1. And now you have this problem that you have to choose what value of epsilon to use. And if you only have, say, 16 digits of precision because you live in the real world rather than in the beautiful abstract arena of mathematics, then you're going to sort of use 10 digits of precision representing 10 to the 10 when you compute this, and you're going to lose a huge amount of precision when you compute the derivative. And you'll have to figure out what epsilon you should even use and how to tune this and all kinds of messes. Furthermore, your neural networks will involve compositions of a huge number of different functions. So this is really just going to be a disaster, and it's not. This is also not what is actually used. So what is used is something called automatic differentiation, which is not a very helpful term. What does automatic differentiation do, and how does it work? Well, in the computer, when this neural network function is computed and the loss is evaluated, by definition, these functions are not just abstractions, but they have to be implemented in some way. The computer is breaking all of the complicated linear algebra and maybe exponentiation and other things that are involved in computing this loss into some set of very, very explicit steps on zeros and ones. And what auto-differentiation does, and does for you very, very conveniently, is essentially apply the chain rule at the level of very, very simple discrete steps. So, I mean, 10 to the 10 plus x squared is something that you could view as the composition of the function x times x, and then the function plus 10 to the 10. And each individual step of that is something which we can very, very easily formulate general rules on how to compute the derivative. And so effectively what auto-differentiation does is it goes through whatever function you write, even if you write it in a very complicated way, not just involving linear algebra. Maybe you want to formulate a function that involves some for loop. Nevertheless, that for loop is something that the computer knows how to algorithmically evaluate in terms of little discrete steps. And autodiff goes through all of those steps, and it figures out how to turn each of those steps into a derivative using the chain rule, and so in that way you're very lucky. This subject is made much easier than it might have been. All you have to do is define what function you want, and the kind of free libraries that you can easily use, TensorFlow and PyTorch being the most commonly used ones, will just compute the derivative for you numerically to arbitrary precision. They do it actually very, very efficiently as well. It's not much more. Computationally, it's not much more computations to compute the derivative as it is just to evaluate the function. And this just sort of all happens automatically. So you don't even really need to know that, but if you ever use any of these techniques, you'll wonder what is it actually doing, and this is what it's doing. Yeah?
How do we know that the loss function is well behaved enough for simple differentiation and gradient descent to work?
We don't. So I mean, that's sort of up to you in terms of the definition of these functions. So a thing that you could do is define some. No one can stop you from, say, making your neural network compute something that's totally discontinuous. And if you do that, it's sort of not recommended. And what will happen is that the derivatives you compute won't be very useful information about how to improve the neural network parameters, and so you won't learn and you won't make very much progress. But at the level of just computing the derivatives, it'll work. It'll just not give you something very interesting. Yeah?
To that point, the max function is not differentiable.
Absolutely. So the max function is not differentiable. It has a point which is not where it's not differentiable. But I mean, pragmatically speaking, real numbers are never exactly zero. I mean, this is just this function, and either you're on this part of the function in which it's very easy to differentiate, or the derivative is zero. And I mean, practically no one cares what happens at that point. Yeah?
Sorry, I think I don't understand. I mean, I know I don't understand, but I don't understand the difference between what you said about auto differentiation. It seems like you said, like, if you have the 10 to the 10 plus x, then you sort of knows this is one thing, this is another thing, and then it calculates each of them numerically. That seems like you sort of have a smart symbolic thing that can tell the difference between how to construct a function, and then it does this finite difference. I mean, it seems like it's I mean, a combination of the other two, right? It's not.
I mean, I think that's fair. Well, so it's never using finite. Finite differences are a terrible idea because there's really a choice of what you make epsilon, and there's just no universal good choice. So what autodiff is using is it's using the chain rule and symbolic differentiation, but after breaking the very complicated looking function into a large number of very simple pieces. So it is just symbolic differentiation, but like if you or I go to compute the symbolic derivative of this, then, I mean, I don't know, we just do it very, very quickly and we say, oh, obviously this doesn't depend on x, this is just 2x. But it has to sort of represent this as some tree of operations where it says, first I take x, and then I make another x, and then I multiply them, and then I add this other thing, and I mean, that's a simple tree, but if for a neural network, it can become very complicated. It breaks it all down into that tree, and it takes the derivatives in each point. And I think there is some clever engineering in terms of making this work. I mean, for something like 10 to the 10 plus x squared, it's very simple. But if you imagine you have like nested loops, like you might wonder, like how does it know what order to do things and whatnot? So I think there's really engineering in this. There's like a whole book about it. But and I certainly am not an expert at that level, but I think it's just good to know that this is what's going on. And it's also a relief. I mean, I don't know. When there's some new subject or some new tool, like there's always a hesitation of, well, I would use this tool, but I can think of these three things that are going to be a huge pain, and I don't want to have to deal with them. So taking derivatives of functions is not one of the things that is a pain that you'll run into if you try to use this in your research or play around with it. It all just happens automatically. Oh yeah, and there's this other word. So, I mean, if you read in the popular press, you might hear words like, oh, like this genius in the 70s or 80s realized that there was this algorithm called back propagation that could be used to train neural networks, and before that no one had any idea, but then some genius came up with something very complicated. So back propagation is, I think it's hard to explain what it is because it's just taking derivatives naively. There's a thing that you could do that I think probably you wouldn't ever be so naive as to do, which is which maybe I won't even bother to explain. But if I have something like w1 times w2 times x, and I want to take the derivative with respect to, and maybe I don't know, maybe I want to do something like this so that it's a little bit more complicated. If I want to take the derivative with respect to say w2, then I first can take the derivative with respect to this object, and then I can apply the chain rule and take the derivative of that object with respect to w2. In other words, I can apply the chain rule. That's all back propagation is. It's just using the chain rule. It's backwards in the sense that if very, very empirically, like on a computer, you want to evaluate the derivative as a numerical thing, something that you need to know if you're applying the chain rule many, many, many times is if you're computing something like h of g of f of x or something, and you need to compute the derivative, I need to compute something like h prime of g of f of x times g prime of f of x times f prime of x or something like this. And that means that in order to evaluate the very first term, I need to know what g is. I need to know what point I'm evaluating at. So that's the sense in which you compute forward, where by forward I mean you apply f, and then you apply g, and then you apply h. So that's moving forward. It's moving sort of outward in terms of what function you apply. And then once I have computed things forward, I can store the value of what g of f was and what f was, and then I can just evaluate the whole derivative by working backwards via the chain rule. So in that sense, you go forward from x all the way to computing h of g of f of x, and then you go backward by computing h prime, and then g prime, and then f prime. So that's the sense in which it's backward. But that's all back propagation is it just you compute the derivative in this way. Since in the neural net case, there are these matrix multiplications in h and g and f, there would be some tensor indices that you're contracting. So there's some linear algebra, but that's really all back propagation is. And it's really just, in some sense, just a restatement of what auto differentiation is doing. So backpropagation isn't a separate thing that you need to learn about this subject. It's just the chain rule that you already know. Okay. So that's some stuff about how this differentiation process works and what some buzzwords mean. Backprop. So there are a couple of other sort of very general things about the subject. One that came up is this issue of overfitting and generalization. So a very surprising fact is that a lot of ML happens with number of parameters much bigger than sort of number of data examples or data points. And this is something that seems very shocking because we're used to, say, thinking that fitting a 10th order polynomial to 3 data points is a disaster and doesn't make any sense at all. And the specific words that are in use are that you're overfitting. If you have way more parameters than you have data points, you would expect to overfit to those data points. And therefore, you're learning some function that, I mean, just to make this very clear, if I fit some 10th order polynomial, I might learn some function that looks like this. And it's very, very unlikely that this function will generalize when I see more data. So that's, if you overfit, then you would expect to fail to generalize because, I don't know, maybe it would be better to fit these data points to this line, or maybe with 3 data points, we just have no idea what's going on yet. If you've only ever seen 3 faces in your life, and that's all you've seen, then you probably don't have a very good model of like what new faces that you haven't seen yet will look like. So this question of overfitting and generalization is a big one in ML. I would say that initially this was completely not understood, I think, in the field why it was that you could be in this regime and still do okay. There are a few reasons why you might think it's okay. There's a very nice paper that explains why this might work in a formal theoretical way that I shared with you by Advani and Sachs. But let me make a few comments that are fairly practical about how to deal with overfitting. So the first point, which is extraordinarily common, everyone is always doing this in the machine learning community, is that you typically divide your data into a training set and a test set. Sometimes people sometimes people say there are 3. Sometimes there's like a training set, a test set, and a validation set, but this is really sort of all we need. And so this would be the data that you actually use for optimization of minimizing the loss function, and you hold this test set out and don't train on it. Now, something that you can observe is you can see what happens as your neural network learns. And so you can plot the loss, which is your objective, as a function of how long you train. And of course, what you expect is to see that the loss is going down in some sort of smooth, good, reliable way as you train more and more. But this solid line might be the training loss. So this is the solid line. You can continuously evaluate how well you're doing on the test set, which is data points that your model has never seen. And so what will typically happen is, for a while, it'll look like, for a while, the test and train loss will be right on top of each other. And during this phase of training, you're learning you're learning information about the data that really generalizes beyond just the training distribution. And then you start to see some divergence. And so here you see some big divergence, and this is a consequence of the fact that you are overfitting to the training set. So the training loss keeps going down, but the test loss stops going down and eventually may go up. So if you have way more parameters than data points, of course, you can memorize the data. This is sort of a very direct representation of what happens when you memorize 3 data points when you have, say, whatever, a 7th order polynomial or 5th order polynomial to represent your data. You've memorized these points since you're not learning anything very useful from them. And as you memorize the training set, you stop doing well on the test set. In fact, you do worse and worse and worse because you're memorizing things that have nothing to do with the test set and don't generalize. So at a practical level, this is extremely useful because if you haven't used this strategy before, because now you can just say, oh, I'm going to stop here. You can just say, I'm going to train for a while until as my training performance improves, and then I'm going to stop when the test performance is at a minimum. And if I stop here, I'm doing quite well on the test set. I'm generalizing pretty well. And that's that. So as a practical matter, this is a very useful tool to make sure that you don't overfit, et cetera. Just separating the data in this way. Now, yeah.
Something really stupid.
Of course.
So if I have, let's say I had 2 tests, so would I always find the same minimum even if I was checking with the second test set? What's the
Great.
What's the error on that?
Absolutely. No, that's a great question. So this is, well, there are several sources of error. So here I'm making a bunch of kind of statistical assumptions in my mind that I'm not making explicit. So I'm imagining, as most people in this field do, that there's some sort of distribution of data that's kind of like there's some universal distribution that all of the data is drawn from. And so I'm drawing the training set from this distribution of data, and I'm also drawing the test set from that distribution of data. But they're separate. They're separate specific examples. So in that philosophy of what's going on, if you have a second test set, you should do almost the same on the second test set. However, if the second test set only has, say, 100 examples in it, then there's some variance of the loss on the second test set. And so I should do sort of roughly the same up to sort of the statistical variance between the 2 test sets. And depending on the problem, you could be in different situations. In a lot of industrial applications, the training set has 1 million of examples, the test set has like a few thousand examples, and so you really don't have to worry very much about that sort of variance or that width around the test set. But of course, if you're in a situation where data is extraordinarily expensive and you have very little data, then that could be an issue. So this is one very practical and useful thing that sort of is almost free. This is also useful because you might wonder, if you start to do this, well, how long should I train? Should I train my network for 100 iterations or 1,000 or 10,000 or 1 million or 100 million? I mean, this gives you an empirical reason to stop at some point for sure. There are a lot of other ways of so maybe this isn't good enough for you. Maybe this isn't sort of a good enough, maybe the performance that you get here isn't that great, and you'd like some way of training longer and getting better performance even though you don't have a lot more data. Yeah?
So in a training set, suppose you have a certain number of data points, which is n, and you are training it with an n2 iterations.
Yeah.
So how the performance varies with n and n2, and which is the most important?
So you're saying, good. So this is a good question. So my training set, you're talking about the training set, right? So the training set has, say, d data points. So there's a question of how long should I train as a function of d? Is that sort of the question that you're asking? Yeah. So in practice,
How long means how many iterations?
how many iterations? So in practice, this is just terminology, but it's sort of useful to know. In the field, a step is sort of one update of parameters. There's another word that you'll see very often, which is an epoch, which is equal to one pass through all the data. So you remember that when I mentioned optimization, I said that typically the practice is to break your data up into batches, which are just randomly resampled, of size, say, B. The batch size is much smaller than D, and you do stochastic gradient descent, meaning that you just compute these, the derivative of the loss with respect to that batch and perform an update based on that batch. So if you were training on the full data set, one step and one epoch would be the same thing because you'd use the entire data set as your batch. But in practice, you never do that. And so one epoch is sort of how long you have to train such that you pass through the entire data set once. Typically, just for reasons that are not, I don't know that there's a fantastic theoretical justification for this. Typically you train for sort of 10 to 100 epochs, just purely as a practical matter. That's typically what is done. Theoretically, you could attempt to justify that, and I mean, I think for very simple, like linear models, you can try to justify that. You could try to justify it by saying, well, this is something where I'm going to start to overfit a little bit, but not too much. So the fact that it's an order 1 number of epochs kind of makes sense. But specifically whether it's 1 or 10 or 100 is just a practical matter. Yeah.
Iteration is like an epoch.
So an iteration. So this is an iteration. So yeah. So a step is one parameter update, which means it uses one batch of data of size. I mean, the batch size might be B, and it's much, much less than D, which is the size of the full data set. So I mean, like in industrial numerology, industrially, like the ImageNet data set has 1 million images. People train with batches that are sort of maybe up to 10,000 images at once, but rarely significantly more than that. And that means the D over B is like 100. So an epoch is like 100 parameter updates. If you go through 100 epochs, that means you have 100 parameter updates for each epoch. So you'd have something like 10,000 steps of training, 10,000 times where you compute the derivative with respect to the parameters and update them. So that's the kind of thing that people use. The extra comments that I wanted to make over here are, what if just this early stopping approach is not good enough for you? Are there other ways that you can avoid overfitting? So avoiding overfitting is usually called regularization. So it's sort of avoiding divergences in loop diagrams is regularization, and avoiding overfitting here is regularization. This is just terminology. And there are two things qualitatively that you might think to do to try to avoid overfitting. One is you want to restrict the class of functions that your neural network can actually represent. In other words, in this example where I have 3 data points and a 7th order polynomial, I have 7 parameters and 3 data points. But if somehow I introduce some correlation or constraint on the coefficients of this polynomial, then I've reduced the amount of freedom I have that's allowing me to overfit these 3 data points. And so you might hope that I learned something that generalizes better. So one strategy is restrict the function class. There's another way of thinking about this, which is fancier sounding but amounts to the same thing, which is I might introduce a prior belief that the function should end up being a simple function. I can say that informally. Formally, I could say as a Bayesian, I might have some prior probability distribution on what kind of function I expect, with simpler functions being preferred. And in that case, I can use that as a constraint. So the very dumb end result of that line of thinking is I can sort of add, say, the sum on ij of wij squared for all I mean, maybe there's an n here for all layers n of my network. In other words, I can take the mod squared summed over every parameter in the neural network, and I can add this to the loss. So in other words, instead of minimizing just the objective, I can also say I have a prior that I think most of the neural network weights should be small, or I think a lot of them should be small and only a few of them should be big. And so I'm going to express that by saying that I'm going to penalize the loss for making these Wij's big, which means, in other words, that there's going to be a pressure to keep them small as well as a pressure to optimize. And this is, in practice, something that people do. And whether this should be squared or just mod or what is basically a matter of choice. This is sometimes called weight decay. So this is a class of things that you might do, and people do that. There's a second set of ideas that you might use to try to fix this problem of overfitting. Instead of restricting the class of functions, I might have the following philosophy. I might think, well, if I'm really going to do well, I shouldn't just do well for exactly the data and exactly the function I have, but my function should be robust. I should get good performance robustly. What does robust good performance mean? Well, it means that if I jitter around my neural network a little bit, if I add some noise, I should still do well. So I can literally do that. I can add noise either to the input data x itself, or more interestingly and effectively, to the neural network parameters themselves while I'm training, with the hope that if I perform well with any kind of noise, then I'm going to only find a solution that generalizes well. And there is a very famous, extraordinarily simple thing that is the most widely used form of noise, which is called, there's something called dropout. So dropout is one of the we'll see many more, ideas that's super trivial and has as many citations as like the supersymmetric standard model or like ADS-CFT. So what dropout is how about I take some fixed percentage of my neural network parameters and set them to 0. I set a different random fixed percentage of the neural network parameters to 0 at every iteration, and that's what I do. That's dropout. So it's really not any more complicated than that. That adds noise because I'm randomly shutting down in these matrices Wij. I'm randomly setting, say, 10% of the entries of the matrix to 0 for each layer when I compute with the neural network. And like I said, at every iteration, I do a different 10%. That works pretty well. There aren't any things that work. There aren't any ideas along the lines of adding noise that work dramatically better than that. It's very simple, and this is one of the most widely used. This is probably the most widely used form of regularization in machine learning, is just doing that. So, I mean, I think the era where you can propose something that silly and get 10,000 citations is probably over, but it might not be, and that's it. So, I mean, adding dropout is something also that, like, you don't even have to, like, you might think, oh, so now I've got to write some code where I, like, say, like, I iterate through these things and I set some of them to 0 each time. This is the kind of thing that is already implemented in any tool that you will use. So you can just say, like, dropout of blah, and it'll just apply dropout to your neural network if you want to, and with whatever percentage you want to set to 0. And training with dropout can help to avoid overfitting. Yeah.
Ask a question about the previous point.
Yeah.
How long you want to train? Suppose you have a new physics model where the new physics model is the signum and the standard model is the background, and so I would think that the number, how long you train would depend on the cross section and the luminosity. So how does that relate to whatever you do here?
Good. So let's try to sharpen the scenario. So what is it that you're training? Are you so you have a model that's trying to learn what the new physics model is, or you're trying to fit?
Yes, I'm trying to learn features for the new physics model.
Okay.
And obviously, I have to learn about the background as well. It's a standard model.
Well, so if you're trying to train a model that's figuring out what the new physics is, then you probably have to train on many scenarios of new physics so that it can learn how to distinguish different scenarios in new physics. And then the question of how big the signal is over the background is going to sort of determine how hard it is to figure out what the new physics is. But I think it might be separate from this question of how long you would train. I mean, the situation of sort of how much new physics, how big the new physics signal is very important in the sort of classical statistical sense of if you're an experimentalist who knows there's new physics, but you're trying to measure, you're trying to set some limit, then it determines sort of how big the signal over noise is, and therefore how confident you can be of the signal. But I'm not sure sort of what the direct translation is in terms of sort of how long you train. Like if you know what the model of new physics is, then you're just kind of doing statistics.
Because overfitting, I can understand, I can naively understand the concept of underfitting in this case, because if you give it too few events, it just doesn't learn anything about the new physics model. So I would think that there is also a certain regime where you overfit instead of underfit. So I'm trying to figure out how, I mean, how it relates to, say, the cross section or the number of events you have.
Well, say you had some, you'd already trained some network that was really smart, and you give it some a million LHC events, and it spits out like the Lagrangian. I think it's possible to do such a thing. I don't know that it would be useful, but I think it's possible. So say you had such a thing. If you then give it only 10 LHC events, then it's probably going to be wildly uncertain about what the new physics is, and it'll just not know with any confidence that there is new physics. But that would be sort of like that would be like a one. Then those 10 events would sort of be like one evaluation of the model, rather than something that you would train the model on. And so the hope would be that the model is sort of trained well enough and it's smart enough that it says, I have huge uncertainties about what the Lagrangian is. It looks to me like it could just be the standard model, and I don't really know. So this is actually kind of an interesting question. I mean, it's sort of an aside, but there's a question of calibration. So we've mentioned that I might want a model that outputs probabilities, and it outputs, like, say, the probability that a digit is a 7, or it outputs the probability that the next word is cat in a sentence. And not only is there a question of how well it performs, but there's a separate question of how well calibrated it is. In other words, if I say that I'm 70% sure that Trump is going to get reelected, if we could run the universe 1,000 times, would he get reelected 700 times and fail to get reelected 300 times? If that's the case, then I'm very well calibrated. If I say 70% and actually it's 800, then I'm sort of not quite as well calibrated. And you can be very, 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 very useful and effective, but be poorly calibrated, right? Like if I tell you, like, the person that you will marry is this person, and the person that and your first child is going to go to this school, if I'm 50% accurate with that, that's really impressive and useful. But I mean, I might not be. But if I say I'm 99% sure of all of those things, then I'm not very well calibrated. So there's a question of, like, when you train these models, do they end up being very well calibrated? That's something that you can just check on the training or the test set. And it's something that you might care about if you're going to really use this model, because you might want to know that its probabilities are useful. Empirically, I think it's often the case that these models end up being fairly well calibrated, but certainly not always.
So
yeah.
Is this a connection between the Bayesian and frequentist description?
Maybe. So I always remember what Bayesian means quite precisely. I'm not ever sure exactly what frequentist means.
Usually think of every experiment sort of as standalone, right? I'm pretty sure, right? So I think it would be like, I don't know, if you were right about the 99% time, okay, let's say you're right the first time, and then you are right, I don't know, 100 times, and then you say, okay, you're well calibrated, but then in other experiments, from now on, you're always wrong, then the frequentist would sort of not know what to do with that. Well, a Bayesian approach just sum everything, I think.
Yeah, so I mean, I think the answer to the question, to the initial question, is yes, maybe, and I don't think I have anything sort of useful and informative to say about it. So I'm happy to discuss it later. But I think it'll sort of be a diversion. So why don't we talk about it later? Okay. So I mean, I often read about this distinction and then I understand it and then I sort of forget it like a month later. Yeah. I'm not sure what you mean.
Like, maybe some type of data more often than likely be overfitted than not. I can't think of anything that hard in it, but is there any intuition beforehand besides for the number of parameters and the number?
Good. So there is some sense of this. So you could have the following, like, I mean, this is a super dumb example, but like, I don't know, say I have a network that has one parameter, and when the parameter is like bigger than 1/2, the model adds the two numbers that you hand it, and when the parameter is less than 1/2, the model like multiplies the two numbers that you added. This is a really stupid contrived example. This is a model which is really, really good at adding and multiplying, and you can extraordinarily rapidly train it. Like, say I like start out with this model, it's super contrived and stupid, and I give it like a couple of multiplication problems, and I start training it, it will immediately realize that it wants to be on the multiplication setting, and then it'll multiply very well. So this model it has a strong bias towards being a calculator that either adds or multiplies. Often in ML, this is called inductive bias. However, if I take a random neural network and I try to, like the kinds that we're drawing that have these matrices, etc., and I try to enter two numbers into it, and I try to train it to add those two numbers that I've entered, or multiply it, I'll have a huge amount, it'll require a huge amount of data for me to get the model to be able to add or multiply with any kind of accuracy, because it's just some general function, and I really, really have to train it a lot to convince it that what it wants to do is add or multiply. So in this situation, the first network it will not overfit. If what I want is to either add or multiply, it will very, very quickly get the idea and do the right thing. If I take the second model and I give it 5 multiplication problems, it will certainly overfit to those 5 multiplication problems and not be able to multiply other numbers that I give it. So there's some sense of inductive bias of like, how much was the neural network as a functional form sort of hand engineered to do the kind of task that I want, and networks that are less well engineered to do the task that I want will have more of an issue of overfitting. And this is really in the philosophy of this first point, that if I constrain the functional form of the neural network a lot to sort of the class of functions I really care about, that I'm sort of doing some of the work, and I'm therefore avoiding overfitting and making overfitting less likely. I mean, in the field, in sort of the grand scheme of things, I think the move is more towards writing down a very universal class of functions and then getting enough data so that you can sort of do anything, rather than hand engineering things. But if you hand engineer, then you'll need less data to do well. Good. So any other questions about generalization and overfitting? Okay, so now I want to talk about, fairly briefly, so, I mean, we're physicists, so whenever you learn about something quite new, it's very, very useful to have an idea of like how big the actual numbers are. So, I'll give a couple of examples. So currently, neural networks tend to have between, say, 10 to the 5 and 10 to the 10 parameters. The upper end of this is really just a question of resources. You can make neural networks with more parameters, and they will typically do better if you just have the budget to run enough computers. So this is something. So this is sort of like 100,000 to like 10 billion scale. I think like the biggest networks that there are papers, like academic papers about, have order sort of 10 billion parameters. So as an example of maybe the most commonly used and talked about data set in ML, ImageNet has order 10 to the 6 images, so 1 million images. They're, I think, at full resolution, although I don't think people always run it to full resolution. They're, I think, 256 by 256. So that means that this has order 10 to the 10 pixels of data in it. And other data sets that are used, so for language, I should say, ImageNet actually is not a big data set anymore. Like 5 or 10 years ago, it was viewed as a very big data set. Now I would say that it's a medium-sized data set. There are data sets in use. There are papers about them that have like order 1 billion images. So I mean, the web has a lot of images. So like you can web scrape Flickr and get like order 1 billion images. And so there are data sets that people train neural networks on with 1 billion, but this is sort of garden variety. In language, data sets for sort of big models typically have something like around also 10 to the 10 words in them. So order 10 billion words. There's like a common crawl data set, which is just lots and lots of text straight from the web that has like 100 billion words in it. But this is sort of the order of magnitude of data sets. And so then there's a question of sort of how much computation is then used to train a neural network. And it's pretty easy to sort of guesstimate this. It's roughly 100 times d times p, where this is p and this is d. Why is that? Well, it's not always true, and sometimes it's more complicated to guess this. But I'm trying to figure out, like, roughly, sort of at the order of magnitude level, how many floating point operations go into training on the data set. So you see the data set. Someone asked about this. You see the data set roughly 10 to 100 times during training, typically. Sometimes you see it 1,000 times if you really train a lot, sometimes less. But this is sort of a guesstimate of this. There are a class of models where this is very direct. You basically use all of the parameters of your neural network on each pixel. So the class of models where that's just totally automatic are these auto-regressive models where you say look at one pixel and then look at the next pixel and the next pixel and the next pixel. And so literally sort of all of the parameters of your neural network do something. They do some simple operation like multiply and add for every pixel. And so that means that you get sort of an order 1 number of operations per parameter per pixel in your data set. And so this for sort of the numbers that we have over here gives you something like 10 to the 10 times 10 to the 10 times 100, which is order 10 to the 22 sort of floating point operations. So, I mean, it's a very remarkable fact about, like, I guess our species that we've been able to build computers that you can run in like a few days that do this many operations. I mean, this is very close to like Avogadro's number. It's a huge, huge number, and we can do it. And this is what's driving all of this progress is really the fact that you could do this. And I mean, I think the predominant reason why this is happening now and not 20 years ago is because of the ability to do this. These operations are, of course, not sequential. They're incredibly parallel. Almost all of these operations can sort of happen in parallel, and that's why this doesn't take forever. But that's the kind of scale at which we're currently at, and this is rapidly growing. So I mean, so this is often measured. I mean, I don't know if often is fair, but this is sometimes measured in petaflop days. Right, so a petaflop is 10 to the 15 floating point operations per second, and so you multiply by a day, which is 24 times 3600, which gives you something like 8.6 times 10 to the 19 operations. And so, I mean, this is something like 100 petaflop days. Petaflops are also relevant because the sort of GPU, state-of-the-art graphics processing units, they used to be graphics processing units that people use for machine learning, can do something like 10 to the 14 floating point operations per second. And so maybe you get 10 of them in a cluster, and you run it for a day. And so this is sort of a useful, actual, practical set of numbers. And so that's sort of where we're at right now. And the biggest sort of training operations that have occurred are things, I think, right now like DeepMind's StarCraft and such, and those use order maybe thousands of petaflop days of computation. The other super interesting comparison about these numbers is that I think a pretty reasonable estimate of the human brain is that it's of order a petaflop. So our brains are running roughly 10 to the 15 operations per second, very in parallel. I mean, this estimate comes from something like 10 to the 10 to the 11, or 10 to the 11 neurons times about 10 to the 4 synapses per neuron, times basically one firing per second. So I mean, synapses typically sort of spike or fire sort of like once per second. So if you imagine there's sort of an order one amount of information sent each time, then this gets you sort of roughly in the petaflop range. So that means that a lifetime of computation is, say, 100 years times 24 times 365 times 3600, which gives you something like 3 times 10 to the 24 operations. So we're in some interesting range where in your whole lifetime, roughly speaking, at the order of magnitude level, your brain does something like 30,000 petaflop days of computation, and the biggest networks that we're training are sort of a factor of 100 or so away from that, and they're sort of very rapid, or maybe only a factor of 10 away from that, and they're rapidly approaching it. So this is sort of interesting. I mean, if you were to take a very, very large-scale view, I mean, as we physicists like to, of the history of sort of trying to do machine learning and AI, you might have picked out specific periods in time when you might have expected something exciting to happen. One of them would have been the first time we built a computer that could run at a petaflop, since human brain compute is a petaflop, and that happened in like the early 90s. So you might have hoped, like, if all you had to do was write the right computer program and then run it to get something that imitated a human brain, then you would have thought that maybe in the early 90s you would get something that could do what humans do. But if your philosophy instead is, I need to train something for order at least a human lifetime to get it to sort of learn all the things that a human learns, then right now is a very exciting time. And then there's the question of, like, how far away are the sort of algorithms you're using from what like, to what extent is it just that you need to train? For example, like, did evolution hard code a lot of really important information into our brains such that we don't actually have to learn it during our lifetime? And if that's the case, if evolution hard coded a huge amount of information, then you'd expect to have to do even more computation than this to be able to imitate human performance. But I think these are interesting numbers, and even just this fact that the numbers are this big is very, very startling. It's Moore's law for 50 years or something. So, yeah.
I think in last week's lecture you said that you usually don't want to have around the same amount of parameters and data. And when I look at these orders of magnitude you gave, it looks like you do have the same amount of parameters and data.
Yeah. So it's okay. You just use this early stopping. So no, this is a good question. I mean, in many cases, so it depends on how you count the data. So for example, the thing that people most often have done historically with ImageNet is classify these images. From that point of view, each image is one data point. Because the image is just, you have this image and then it's either a cat or a lawnmower or whatever, and that's sort of one fact. If you count it in terms of pixels because you're trying to make images, then you might count it more naturally with pixels. The regularization part of this sort of avoids a lot of these in principle problems with having exactly the same number of data points as parameters. But this is a good question. Other questions about? Yeah.
Is there anything you can comment about quantum computing?
I don't know very much about it, and what I do know is not very optimistic, but I don't have anything very concrete to say. I mean, what I know at a fairly technical level is basically limited to the fact that Adam Brown gave a sort of journal club talk, I don't know, 6 months or a year ago about this subject, like what can quantum computers do for machine learning. And it was a very enjoyable talk because he made fun of the fact that quantum computing is so hot and machine learning is also so hot. So if you can bring them together, it's like the hottest thing in the world. It was really funny, but especially because he has such a wonderful British accent. But I think his conclusion was that there weren't really very many ideas that could really use quantum computers to sort of speed most of these things up. And then there's also the fact that, I mean, I don't know, but I mean, quantum computers are not actually sort of there yet. So I don't know of anything that's super optimistic, but I might just not know. I mean, I think the basic problem is like, the first thing you might think, at least if you're as naive as I am about quantum computing, is like, oh, well, like maybe quantum computing is very parallel, and so you can do a lot of things in parallel. But I think quantum computing is really a lot more complicated than that, and it's not just as simple as you can just sort of make parallel things happen. And so there's really a lot of challenge in sort of in doing these things. Maybe just one brief comment. So what are the open problems in this field? This is sort of beside the point, but basically almost all of the open problems in the field empirically come down to the question of sample efficiency, which is, in other words, like, how can I get incredibly good performance with much less data? There are a lot of, so you can phrase this in much more interesting sounding ways. Like you can say, well, how can I get a neural network that learns how to play one Atari game and then uses that information to play another Atari game? So that's transfer learning. You can talk about generalization in a more interesting way by talking about like to what extent do neural networks extrapolate from what they have learned to like some new data distribution. But ultimately this all comes down to sort of how can you make neural networks, AI, learn with a much smaller sample size because of the fact that we know that humans use less data than machine learning algorithms to learn to do the things that we do. And we don't know if that's because our algorithms in machine learning are wrong. We don't know if it's just because the neural networks we're studying aren't big enough. The neural networks we study are sort of like the 10 to the 10 parameter neural network in some sense is sort of like a factor of 1,000 or 10,000 times smaller than the human brain in terms of like what you'd guesstimate as the number of parameters. So maybe we just need bigger, more powerful networks. Or maybe we need some new technique for training them, whatever. But kind of all of the open problems that I think people are most focused on in this field are associated with this idea. Yeah.
Do you know the class of functions that you can get out of a neural network? Is that known? Like, can you get any function out of a neural network?
So I don't think that there's very much that's practically useful that's known about this. There are formal mathematical results that say that like neural networks of certain shapes can produce, like in a limit, can produce any function. But I don't think that that's that relevant to what you're actually getting out. And then for the actual systems that people use, I think not that much is known. Yeah.
Just on that point.
Yeah.
Are there any formal mathematical results to do with processes? So for example, for adding noise, you're talking about this
Yeah.
Clearly works, but it seems rather arbitrary.
Absolutely.
Do people, is there a theory of machine learning where people prove optimal strategies for doing these separate steps?
So I mean, like, there's some stuff along those lines. I mean, something that I said in the first lecture that I believe is the case is that there's a huge opportunity for people with sort of a physics-ish background in this field, because I think most of the work is either very engineering-oriented or too formal, and there isn't a lot of like toy model building that sort of really addresses the sort of experimental result, like how these models are performing, but without sort of the constraint of, say, mathematical rigor. I mean, it just culturally, the papers on theoretical machine learning are sort of in the style of theorem proof, so there are. But there are interesting results. I mean, for linearized networks, you can show that dropout turns into, in expectation, the same thing as this sort of weight decay. So like if your model is just a linear model, that's true. So that gives you some intuition. So there are a lot of nice results like that where you can get some intuition where you take a very simple model and see what would happen. That's also true of this Advani Sachs paper that I mentioned a couple of times, that they explain why having either way fewer parameters than data points or way more parameters than data points are both sort of okay things to do. It's very nice. It turns into some statement about the eigenvalues of a random matrix, and whether or not those eigenvalues are close to 0. So there are very nice things like this. There are a few other nice things, like there's this infinite width limit of neural networks. I mean, the neural networks we study have a width of order 100 or 1,000, so maybe that's a big number and you can expand in it. And I think that's quite reasonable. And there are really nice results about how things simplify in the infinite width limit. And then that gives you something more tractable. So those are some examples. But I think there's way more that isn't understood than that is. And I think even in these limits, some more detailed things I know suggest that, like, the infinite width limit is a very interesting simplifying limit, but it seems like, for reasons I can explain, that you're sort of like not that close to that limit. If you think that limit is sort of like the very perturbative limit, you're kind of like at coupling order 1 instead of order 0, instead of close to 0. But yeah, I think there's a lot of effort, and I think there's a ton of opportunity. Yeah.
Just a question on the sample efficiency.
Yeah.
Is it that clear that humans have a lot less sampling? Because, like, if I wanted to teach a baby to recognize a cat, for instance, I might put a cat in a room with a baby, and then that baby is just continuously getting pictures of cats. I mean, it's the same cat, but the child would probably have some, on top of that, some object recognition type of thing to be able to distinguish that, like, yes, in this blank room controlled room that I keep that this object is a cat, and then they can, like, recognize that different from all the other objects, which is something that machines already have trouble with like machine vision. So I mean, is it?
I think it's clear at the order of magnitude level in the sense that I mean, these things are constantly improving, but I think that for most tasks you need several orders of magnitude more data for the ML algorithm to sort of do really well than you would estimate a human needs. I think there's some very specific tasks where maybe it's not so different, but I think it is. I mean, maybe the starkest example, I don't know. I mean, there are confounders for all of this, but I mean, like, robotics doesn't really use machine learning at all. Like, I mean, like, I don't know, there's this like Boston Dynamics company that builds these impressive looking robots. They don't use machine learning because it's sort of too slow to learn. If you can learn in a simulation, like you can learn to play Atari and you can play 100 Atari games at once and you can play them at superhuman speed, and then like in a day you learn to play Atari really well. But if you have a robot that's moving around in the real world, like we learn to walk in the real world without walking in a simulation, it seems. But like that's not a thing that, like, you can't get human level dexterity or mobility with the kind of sample efficiency we have. And this is confounded because you say, well, like dogs are born and they basically walk immediately, so clearly like our brains are partially hard-coded to do this, and so you can ask, well, maybe that's why we're so much more efficient, and you can argue a lot. There's a similar argument you can have about language. We definitely see fewer, like I said, there was something like 10 to the 10 words in this data set, and I think you can estimate, like, even if you're kind of talking all day, every day, or exposed to that every day from birth, I think you see, like, several orders of magnitude fewer words, and yet you learn to use language. And this is also could be confounded by lots of things, but these are the kinds of reasons why people believe we are much more sample efficient than current ML.
Well, just on the subject, are there efforts to have some continuous learning where, like, maybe you don't analyze a picture for the full set of parameters, but you just have you quickly glance at a picture and it kind of slants everything to learn what is in that picture? I mean, I feel like that's more close to what people do. Where, I don't hear.
Yeah, that's sort of like unsupervised learning. I mean, that's something that we do, but yeah, I don't think there's any sort of simple like solution to this right now. The simplest solution that I know is maybe you just make the networks bigger and they become more and more sample efficient. That's empirically what we actually see, although it's not sort of a well-known fact really. But just by making the networks bigger and more powerful, they become more sample efficient. So if there was something that just solves it in a simple way, that might be it. But I don't know that that's enough either. Any other questions? Yeah.
We keep on playing a little fast and loose with terminology here, calling these things neural networks, and then inferring that there's an immediate relationship to how a human brain works.
Oh no, there's no. If I did that, I didn't mean that at all, actually. But yeah.
Comparing a number of operations and such.
Oh sure.
Is there a sense in which the actual architecture of the neural network that is the brain is it all similar? Can you make a statement about like how many layers typical computation will go through in the human brain versus the computational network?
That's a good question. I think I don't know the answer. Maybe someone does.
I think the answer is around 10. You can calculate it from signal response first. For example, when you feel a touch or something, it takes order of magnitude a second, and one layer in the brain I think is measured to be like a tenth of a second. So you infer about 10 layers of computation.
Yeah, I think that kind of thing seems fair. Yeah, it depends on what the operation is, but yeah, I mean in terms of like image recognition or just something that's a very immediate thing, I think that seems fair. But I mean, I guess the reason why I didn't say very much was that like in your brain, presumably there are all sorts of cycles, and in a lot of the neural networks we're studying, we don't have cycles, for example. Like it's sort of like signal goes in, it gets processed some amount, and then it goes out, and it doesn't like come back in necessarily. Now, I mean, there are networks where it does, but yeah. Okay, so I guess in the last sort of, I don't know, I have 15 minutes or so, I'm going to sort of quickly give you pragmatic information about optimization. So, I mean, in some sense, for the most part, all there really is pragmatic information, because I don't think that there is a good sort of theory of this that is addressing the pragmatics of it. In other words, people try stuff and it seems to work, and they're very constrained by wanting to be computationally efficient. And there are mathematicians who are now working on trying to understand why it is that the things that we try work, but I don't think that we really know. So, I mean, I mentioned before that there's this sort of gradient descent rule where we can iteratively, discretely update our parameters. So this is like the loss is a function of the parameters in the data, and we compute the gradient, and this is stochastic gradient descent, where it's stochastic because we sample a mini batch of the data rather than the full data set. So that's a thing that you can do, but it's not. So there are a bunch of different things that you can complain about, or that you can worry about with this. One thing that I sort of am not going to solve, but I think is worth mentioning, and of course we're physicists, so we should, is you can look at dimensional analysis. By which I just mean I have these neural network parameters theta, which have units of parameter, and I have a loss which has units of loss. And so from that point of view, this has units of parameter and this has units of parameter. This has units of loss over parameter. And so that means that epsilon has units of parameter squared over loss. Now, I mean, this could bother you or not. There's a lot that you can say about all of this that I'm not going to have time to talk about. I mean, you can read about it in my notes or many other places. But a thing that might bother you if you're very, very theoretically minded is that the parameters are, there's no natural metric that is in use right here for parameters. So like, I mean, there's no reason why I can't rescale all of my parameters by a factor of 10 or write my matrices in some sort of like polar coordinate like matrix decomposition, or I can write my matrices W in some factorized form as like U du transpose or something like that. And then I'll really be redefining what my parameters mean. And this is not in any way nicely covariant, and what that means is that sort of the value of epsilon I choose for one parameterization will not be natural in another. And this is sort of related to the fact that this has these units. There is a thing that you can do which has the right units. So if you use Newton's method, then the parameter update would be Hessian inverse times grad L, where the Hessian is d theta I d theta j of the loss. And now this has units of loss over parameters squared, and this has units of loss over parameters, but this is the inverse of this matrix. So this naturally has units of parameter. And so that's really great. However, for reasons that I mentioned last time, we don't use this because computing the Hessian and then computing the inverse of the Hessian is just very computationally intensive, and so we don't do it. But there are alternatives. This would make sense. There's another alternative that makes sense that's called natural gradients, which you might want to learn about just because it's nice, it's actually elegant, where instead of the Hessian, you use the Fisher information matrix, which also has the same units, and there's a sense in which that's really a very natural thing to do. What you're then doing is you're doing something that is actually coordinate covariant. So in other words, if you change from some parameterization of these matrices with their entries to some other parameterization, this changes, but natural gradients are actually covariant. So that, if you're a physicist, is very satisfying. Once again, somewhat unfortunately, sort of, so in natural gradients, you have sort of this Fisher inverse grad L. The Fisher also has this problem that it's hard to compute, but it's actually not quite as hard to compute as the Hessian. It also has another nice feature, so something you could complain about this is that since we're studying a non-convex problem, the Hessian has both positive and negative eigenvalues, and it could have eigenvalues that are 0, and then this sort of is problematic. But the Fisher is always positive definite, and so this sort of completely makes sense. And there is some set of algorithms called KFAC, it's just some acronym, which is some very efficient way of trying to estimate this. And people use that a little bit. And it is quite natural. It has the right units. It's invariant to how you parameterize the network. And so that has caused me to sort of go off on a tangent and tell you about it. So these are some things that would be natural. Gradient descent isn't natural. I'm going to tell you the thing that now is actually used by people by far the most, which is still not natural. It's slightly more natural. So what are the problems that we encounter in just using this? Well, besides this theoretical issue, there's sort of a practical issue of ill conditioning. So that's this issue that if my loss landscape looks like this, then I might be bouncing around back and forth in here, but I'm moving very, very, very slowly in this other direction where the potential or the loss is very shallow. So there are two ideas that you can use to try to make this better, and the atom optimizer uses those two ideas. So now, first of all, you want to sort of tie your hands behind your back by saying, I don't ever want to use anything other than the first derivative of the loss with respect to the parameters, because computing higher derivatives is just too inefficient. So all you have access to are the first derivatives. So all you have access to are sort of subsequent versions of this object. So what can you do? Well, one thing I mentioned that you can do is you can, this idea that is called momentum, which is you can define some, I guess I'll write it out formally. You can define some velocity vector v, vi, which is which has an update rule where vi n plus 1 where vi n plus 1 is some number m times vi n plus the next gradient so here m is some number like 0.9. It's a number between 0 and 1. And so the idea here is that as you start in some place in the loss landscape, you start off with, say, v being 0. You keep 90% of your last v plus you add the next gradient. And so all this is doing is this is a way of accumulating some moving average that's spread over sort of 1 over 1 minus m of the last steps, roughly speaking. This is some exponential moving average of the gradients. And why would this help? Well, you might hope that this helps because if you're bouncing back and forth in this direction, but consistently moving in the other direction, then you get an additive effect in this direction, whereas you get a canceling out in this other direction. And so you might hope that that leads you to sort of mostly move more in that direction. And there's some rigorous sense in which if you have a convex potential, you have a convex loss, and it's fixed and deterministic, you can actually prove that this really does help in this way. And there's a really, really beautiful paper slash like sort of interactive blog post that explains this if you're curious. But there's another thing we can do, which is we're not limited to just say addition. We can also use, we can square things, we can divide, etc. And so you can define another thing. So I don't know, maybe I'll call these things di. You can define some things di, which are the accumulation of the square of the gradient components. So I'll introduce some other parameter beta. And so these things that I decided to call di are just, they're basically the same as this momentum, except I'm accumulating the square of the gradient components. So why would I do that? Well, I mean, it's an ad hoc thing, so I don't know. But a reason why I might do that is sort of the same story that I just told for momentum, which is that if my gradients tend to be moving back and forth, then I'm not really making progress in that direction, and so I'd like to suppress it. But if they're going in the same direction, then I don't want to suppress them as much. So I can now define an update rule, which is that theta I n plus 1 will be theta I n minus some learning rate times the VIN over the square root of DI. Right. So this is very slightly complicated. I'm using momentum to compute the gradient. It doesn't really matter. There's another thing where I could have just made this be the gradient at the nth step if I wanted. Then I would have something that has the useful name RMS prop. But the thing that's actually typically used is atom, which uses momentum for this. So it's this thing in the numerator. So this is sort of a smeared accumulated gradient for like maybe the last 10 steps. This thing for the ith component is the accumulated sum of squares of the last many, many steps. So typically this parameter beta is sort of like 0.999 or something like that. So this accumulates the square of the gradient over, say, the last 1,000 steps. So if in a particular component direction I've been oscillating back and forth a lot lately, then this number will be really big, even though the accumulated gradient will be quite small because it's mostly canceling itself out. And so this will be fairly small, and this will further suppress it. Whereas if I'm moving very smoothly but slowly in this direction, the accumulated square of the gradient in that direction will be not so big, and the accumulated gradient itself will be as big as it can be because I'm getting constructive interference, and so I'll sort of move quickly in that direction. So this has this weird property. So now what are the units of this? So this has units of gradient, which is has units of loss over param, and D has units of loss squared over param squared. So when I take the square root, this is actually just some dimensionless number. That means that epsilon just has units of parameters. So in this optimization, this has units of just params. And so what this means is that if all of the gradients of one component point all in the same direction over and over and over again, this is basically just going to be 1. And so I'm just going to update the parameter consistently by epsilon. But if I'm getting oscillation back and forth, this will be a lot smaller. So this has this weird feature that no matter how big the gradient gets, I'm never going to update myself by more than epsilon because of this cancellation. But if the gradient is very inconsistent, I update a lot less. So this is a completely ad hoc thing. You can ask, for example, why is this a square root? Why isn't it the 2/3 power or the 1/3 power or something else? And no one knows. It's even possible that using some other power is slightly better, but it's at least not enough better that people have discovered that they should bother to use it. So this is basically just ad hoc, but it's another paper that has as many citations as like ADS-CFT. It is called the Atom Optimizer, and this is what I recommend you use if you make a neural network and you go to train it. You of course don't, like everything else that has thousands of citations, you don't have to like write these equations down and implement them. You can just say use Atom Optimizer library that I'm referencing and it will do it. But this is what the Atom Optimizer is doing, and it'll always do sort of at least an order 1 factor better than just plain gradient descent. Yeah. Yeah, my apologies. So epsilon is just sort of the typical thing that's used for like the learning rate, which people just mean like the number in front of this. But yeah, this epsilon has different units, and maybe the best value to choose is different from here where in the Atom Optimizer. Yeah, people typically call both of them the learning rate. This is just terminology. It's just sort of it's some scalar factor that sets the size of these discrete steps. I mean, people don't usually change beta during training, but you can use, so these are all, both M and beta are things that you can decide what you want to use for them. So in terms of like pragmatic suggestions, the thing that I would recommend screwing around with is the learning rate in all of these cases. The default values for M and beta usually work pretty well all of the time. You definitely can screw around with them, but so things like beta and epsilon and M are called hyperparameters. Basically anything that isn't a learned parameter like the neural network weights, but that is something you can choose and you might do get different results is called a hyperparameter. And there are, of course, tons of them because here there's beta and M and epsilon. If you say use regularization like dropout, that's another hyperparameter, like how much dropout do you use? In a certain sense, you can think of like what neural network you choose or what the shape of it is, like how wide it is versus how deep it is as a hyperparameter. So those are all things that like maybe if you get the hyperparameters right, you do a lot better than if you get them wrong. And this is a huge kind of bugbear for the machine learning community in the sense that like when someone writes a paper and says, look, I did really awesome at this task, like I'm so much better than everyone else, a very common thing is that like they didn't sort of tune hyperparameters in a fair way. So for example, like a thing that very often happens is someone writes a paper and they say, oh, look, my algorithm is 3 times better than old famous algorithm. And what happened was they tuned the hyperparameters for their new algorithm very, very carefully, but they just took some like random choice for the old algorithm and they said, oh, I did way better. And then it turns out that like if you tune hyperparameters for the old algorithm, then you could have done better than their new algorithm. So this is a huge annoyance in the community, but it's just some sort of practical problem. But practically, I would just recommend you use the defaults for everything except this, and then you just use Atom out of the box for problems that you want to train on. Yeah.
Is any of this related to what is known as annealing?
So annealing, so a thing that people also do is let epsilon depend on time in the sense that early on they use a different value of the learning rate than later on. Specifically what they typically do is take a large value of epsilon early and then slowly decrease it. That is annealing. Because what's happening is that like first you're taking big discrete steps, but then you start taking smaller and smaller steps, and so you can kind of like find your way into like some minimum of the loss, which is some kind of like nook and cranny that requires small steps to get to. So that I think is what annealing is, and so that is sort of most directly related to annealing, is having a schedule for epsilon. But you don't really need that to do pretty well, and it's an added complication. I mean, there are other physics things to say about this whole process. So there's a sense in which the ratio of epsilon over, well, for this, epsilon divided by the batch size is kind of like a notion of temperature. Because what you're doing here is you're sort of like jumping around. And if you make epsilon bigger, you're taking bigger steps, which means you're fluctuating more. So roughly speaking, epsilon is kind of like a temperature. That analogy is definitely useful at some level, but it's not so important that I want to spend like 20 or 30 minutes going through it. But there are like many other insights here. I'm just very constrained by time, and so I should stop here.
Any further questions or comments?
Well, I thought that annealing, maybe my understanding is wrong, but so you learn something, you get into a minimum.
Yeah.
Don't know it's a global minimum or not. So what we do is we just basically warm it up and let it learn again, and then we see if you go to the same place or not.
Yeah. So here you're never ever in a global minimum, or at least you're never in a unique global minimum. The minima here are sort of very, very non-unique. You could do that. So that's absolutely a thing that you do in this, if you want to sort of check what the variance is in performance. You can sort of start over and retrain. So that's definitely a thing that people do. I think typically a thing that you're trying to maximize, at least if you're in this field, is you're trying to maximize performance as a function of sort of how much computation you did. And so rather than take the same model and start over, say 100 times and see what's best, that costs you a factor of 100 times more computation. You'd probably rather spend that 100 making one bigger model and just training it once, you'll probably do a lot better. But certainly, like, if you're trying to do experiments, like you're trying to figure out how reliably something is helping, then that's something that you would do. Yeah?
In the gradient descent method, you said there's a problem with epsilon because it has weird units. But can't you just normalize the gradient, take it as the direction of the gradient, and then epsilon will have units of parameters?
Yeah, so this is almost like that, right? But this is sort of smoothing it out and accumulating it because it's sort of using whether or not the gradient is sort of pointing in the same direction over multiple steps. Maybe one other thing I should just mention, just to emphasize how dumb this is not at all basis independent because these are the actual components of the vector. I mean, you're doing violence to linear algebra here. So like if you have a gradient vector that happens to align with the axes that you're using, you get a very different answer than if it's sort of like misaligned with the axes. So just to emphasize, this is not the norm of the gradient vector. This is the square of each individual component of the gradient vector. Not a thing that mathematicians would smile at.
So why is that a problem that epsilon has units in the gradient descent method? I mean, I understand why this method is better than this one, but I don't understand this argument with the units of epsilon.
Well, I mean, if you're someone who likes beautiful things, a thing you might like is to be able to sort of either set epsilon to 1 or set one value of epsilon and have it work for every problem you ever encounter. And if you use something like natural gradients, you might hope that that's actually achievable because natural gradients, epsilon has no units. So no matter what the normalization of your parameters or the sort of parameterization of your parameters, you might hope that you sort of are getting the same thing every time. Whereas in this situation, you really just, it depends on, like you have to scale epsilon depending on how many parameters you have, what the scale of these parameters is, like all kinds of other things. So just, it's something you have to think about, whereas you might like there to be a way of doing things where you just set it once and never have to think about it again because it takes a natural value. So the fact that it has units means there's no natural value for it. Yeah?
I mentioned this before, but for dropout, so is that as a sort of like the hyperparameter, is that something that you recommend? And I said it's a few percent. Is that something that you recommend playing pragmatically speaking around, or is there sort of a fixed a good value for that?
I mean, I think the sort of default value that people typically use is like 10%. That, I mean, like it really depends on how much overfitting is a problem for you. So I mean, I mean, if overfitting isn't a problem, I would recommend not using dropout. And then if you're really worried about overfitting, you're encountering it, then you can just try making it bigger. I would start with the default, and you can try cranking it up. The problem with dropout is that if you make dropout bigger, it'll make learning slower because like there's a lot more noise in the learning process. So then you'll have to wait longer to get results. But anyway, yeah, I would just fiddle around with it.